By the way, if you were perturbed at all by my previous talk, this talk essentially doesn't depend on the previous talk at all. It does depend on the first two talks, however. So the goal today is to show that there's a Borel probability measure on the Berkovich projective line, and I'll remind you what those things mean, supported on the Berkovich-Julia set, in fact, with support exactly equal to the Berkovich-Julia set, and invariant under the map. I'll say what that means too. So this has been done over the complex numbers, I don't know, in the 80s or 90s or something like that, due to Brolin, Lyubich, various other people. So the idea is a measure whose support is exactly the Julia set. So I'll need to give some background on measures, potential theory, and a little ergodic theory. Some of this stuff has been touched upon in Manfred's and Sound's talks, but I'll say a little more about it. So let me just start with some basic stuff about measures. So take any topological space. You should be thinking either the Berkovich projective line or the Riemann sphere, an assigned Borel measure on X. I'll remind you what that means in a second. And take a measurable function, and you should be, from the space to itself, you should be thinking, just a rational function. So Borel here, of course, means a measure with respect to the Borel sigma algebra, which is the one you get from open sets, and then taking complements and countable unions as many times as you want. A signed measure means it's the difference of two usual measures, two non-negative valued measures, but because you have to worry about infinity minus infinity, implicit when you talk about a signed measure is the measure of any set is finite. Well, for my purposes anyhow. All right, so given a measure, the push forward measure by this measure by the measurable function phi is a signed Borel measure where you take the measure of a given set, a given measurable set is the old measure of the inverse image of that set. Or if you like to do things in terms of, think of measures in terms of integrals, then the integral of a function with respect to the new measure is the integral of f composed with phi with respect to the old measure, equivalently. So this is an easy exercise to check that these two definitions of the measure are equivalent. And if mu is a probability measure, and just to remind you, that means it's a non-negative valued measure where the measure of the whole space is exactly 1. And so the idea is that the measure of a given set is sort of a probability that at some randomly chosen point actually lies in that subset. So if you have a probability measure, then the push forward of it is also a probability measure. That's, again, easy to check. I'll say a little bit more about what these are in a second, so don't worry if you didn't absorb the full slide in 1 second. Oh, one other thing, it's indicated with this lower star, and it is functorial, covariantly functorial. If you compose two functions and push forward by the composition, that's the same as pushing forward the measure by each one successively in the same order. You can also do pull-back measures. To do this, you can't do this on an arbitrary topological space. So now I'm specifically going to be talking about the Riemann sphere or Berkovich space. Phi is going to be a rational function, non-constant rational function. So given, again, a signed Borel measure mu, the pull-back measure of it is, well, this one's harder to define in terms of the measure of an open set. All right, this looks like a mess. So the key thing that's happening here is I'm summing over all y's now in the inverse image of x. And each of those y's therefore maps to x under phi with some multiplicity. So again, for Berkovich points, if this is a type 1 point, the multiplicity is just, the multiplicity with which the function maps that point. If it's a critical point, it maps with higher multiplicity. If it's not a critical point, it maps with multiplicity 1. And if you recall, a couple lectures ago, I had this notion of what it means for say a type 2 point to map with higher multiplicity. You don't need to remember what that definition is, but there is some notion of a point of any Berkovich type mapping with multiplicity to its image. So the total of all these degrees, all these local multiplicities, is always d, the degree of the map. So I'm just summing over all. Most of the time, you're going to have d distinct pre-images. I mean, every now and then you get multiplicity. So the idea is you're sort of summing over all the d distinct pre-images of x. And you're evaluating the function at each of those d distinct pre-images, and you're integrating that resulting integral with respect to the original measure. But of course, in reality, all the pre-images aren't always distinct, so you need to do this funky sum. So the idea is you're just summing over all the pre-images of the values of the function and integrating with respect to the old measure. That's declared to be integrating with respect to the new measure. So just to compare that, so that's the pull-back measure. If you integrate with respect to that, you're summing over all the d backwards images. With the push forward measure, there's only one forward image of the point, and you evaluate the function there. So it's sort of parallel to the definition for the push forward measure. If you wanted to define what the pullback measure of a given open set is, well, just take this definition, but put in for f, take the characteristic function of, well, that's what this boldface 1 means here. Take the characteristic function of the set. It doesn't have a nice, simple way of understanding what that means like it did for the pullback measure. For the pullback measure, the measure of a set was just the measure of the inverse image of that set. There's not quite as nice a description. Oh well, that's life. So the pullback measure is a little bit more complicated to define, but once you get used to it, it's not too bad. And I'll say more about it in a second. Please note, this one does not preserve the total measure. So for example, if mu is a probability measure, I mean, you're summing over d pre-images. So the full measure of the new thing is d times as big as it was before. So if mu is a probability measure, the pullback of it is not a probability measure. You need to divide by the degree of the map, and then you get a probability measure. Again, that means non-negative valued total mass 1. And this one, as the upper star suggests, is a contravariant thing. So if you have if you pull back by a composition, it's pulling back by the two maps one at a time, in the opposite order. Okay, now to help you understand these a little bit better, you can sort of forget what the original definitions were a little bit by remembering a few of these properties. So the support of the push forward measure is the image of the support of the original measure. Again, this is a relatively easy exercise. I'm actually not 100% sure I have this right, but if this is not, I think it's true, but if it's not 100% true, it's sort of morally speaking true. So, but anyhow, the support of the pullback is the inverse image of the support. So that's sort of the idea of what the push forward and pullback are doing. Even more so, you can be really explicit about what these things are if you're dealing with delta measures. So of course, delta measures, I think, are the easiest measures to understand. You know, the delta measure at a point A is just the measure of a set is 1 if it contains A and 0 if it doesn't contain A. So these are really easy measures to consider. Well, the push forward measure of the delta measure at A is the delta measure at phi of A. So that's easy to understand. And the pullback of the delta measure at A is you sum over, again, with multiplicities, because you need that technically, is the sum of the delta measures at all of the pre-images. So these are this is, I think, this is the way you really understand what a pullback measure is. The pullback of a delta measure is just take the inverse image of all those, of that particular point. So actually, this is actually very much like, you know, when you learn Weil divisors in algebraic geometry, the pullback of a Weil divisor by a given morphism is exactly this kind of thing. You sum the guys in the pre-image with multiplicity. Only this is more general than you can do the pullback of an arbitrary measure, not just a delta measure. So it's a little more general than the Weil divisor idea. It's easy to check, also another fairly straightforward exercise from the definitions on the previous slides, that if you do the push forward of the pullback of a given measure, you just get the measure you started with back, but multiplied by the degree, again, because the pullback sort of multiplies the total weight by the degree. All right, this looks like a weird property, but this actually turns out to be very important. This is an if-then statement, and both the if and the then seem like sort of so what kind of conditions. So if phi and mu are related by this amazing coincidence that the pullback of mu is exactly the degree of phi times mu, if they happen to be related that way, then the push forward of mu is exactly equal to mu. So I'll say a word in a second about why we might care about that. But first of all, the reason for that is just automatic from the previous line. You just sort of take push forward of both sides of the measure on both sides of this equation. And if you believe the previous line, then this guy just falls out immediately. So the reason we care about that is very shortly, and the main topic of this talk is going to be to prove that there is a mu that has, given a rational function phi, there's a mu that has this property, a measure that has this property. And so the point is, for free then, once you have this property, you get that you have this property. Okay, so what? Why do we care about this property? Well, as Manfred could tell you, and as I believe he did tell you, ergodic theorists get really excited when you have this property, because that's called the measure mu is said to be invariant with respect to the map. Or if you think if mu is your central object, you say that the map is measure preserving with respect to the measure. It just means that this property just means that the push forward of mu is mu, or again, in the original definition, the way it's normally stated in the ergodic theory book is that the measure of the inverse image of u is mu of u. So the point is, this is a good property if you like ergodic theory. So the point is, we're going to prove that our measure we're going to construct is going to have this property. So that means it's invariant. Okay, great. So here's the big theorem, which was proven independently by various people, I don't know, 6 years ago or something like that. So Charles Favre and Juan Rivera-Letelier did something with it. Matt Baker and Bob Grumley had a slightly different strategy, but these two strategies were closely related. Antoine Chambard-Loire, along with his student Amaury Touillet, did it along with they used some work of Pascal Tissier. So this was all, but their proof used more intersection theory, but all the proofs are sort of closely related and use a lot of the ideas that I'm going to get to in the coming few minutes. So it says, given a non-Archimedean field and a rational function defined over it of degree at least 2, so the usual situation I've been working with in these talks, then they show that there is a unique probability measure, again, so a measure that's non-negative valued and total mass 1 on the Berkovich space, that has this property. So this first property is exactly the property I was touting on the previous slide. The pullback of mu is exactly the degree times mu. So it's very nice with respect to pullbacks. And now this is talked about in the notes. I haven't mentioned it in these talks yet, but there is this thing called the exceptional set of a map. The exceptional set of a map is simply the set of points for which, if you look at their backwards orbit, the set of all points that ultimately land on it, that's a finite set. This is rare. If you have a polynomial, the point at infinity is exceptional because the only inverse images of infinity are infinity itself. There are some other maps that have slightly larger exceptional sets, but basically the exceptional set is essentially at most 2 points, and usually it's empty. So the exceptional set is just a couple of stupid points that you don't really want involved. The reason I'm throwing this in here is to make sure we get uniqueness. So for example, if you wanted to have this property true, if phi were a polynomial, which has the point at infinity is totally invariant, you could just make mu be the delta mass at the point at infinity. And then if you take the pullback of the delta mass at infinity, well, the inverse image of infinity is d copies of infinity. So you just get d copies of the delta mass. So this would be stupidly true if phi were a polynomial and mu were the delta mass at infinity. But we sort of don't want that. That's too boring because all polynomials have that. That's not, and they have, even though all polynomials have massively different dynamics, it's just sort of a stupid thing that uses this stupid party trick that the point happens to be in the exceptional set. So if we, question?
Yeah, I was just wondering if you can address the type 1 later.
Oh, yeah, no, I could, but not in, yeah, I'll talk to you about it afterwards. There is a notion of a type 2 exceptional point, but those actually don't matter. It's going to turn out if you have a type 2 exceptional point, that's not going to be a problem. But yeah, so it's only the type 1 exceptional points that will be a problem. Basically, because it turns out if you have a type 2 exceptional point, you actually do want that to be the invariant measure. Okay, so again, really this second condition is just to avoid the possibility of stupid party tricks. I mean, it's really the first condition is the one that we care about here. Okay, so the point is, what they're showing is that there is an invariant measure that's somehow very natural with respect to the map. And it has more properties. Its support is exactly the Berkovich-Julia set. I'm not going to prove that today, but that's not the hard part of the proof. Once you have the various other properties, that sort of falls out without too much work. And it's also strong mixing and hence ergodic. I don't expect you to know what either of those things mean. So let me tell you what they are. Again, Manfred mentioned what ergodic means. It means, so first of all, it means, by the way, here I'm talking about an invariant measure that is a probability measure. So ergodic means that if you have a set that's also invariant, again, the way Manfred described it was, sort of morally speaking, it's either empty or the full set. Well, morally speaking with respect to the measure. So either it has measure 0 or it has full measure. And by the way, you should be keeping in mind here, that makes sense in this case, because if you recall, the inverse image of the Julia set is the Julia set, and the inverse image of its complement, the Fatou set, is the Fatou set. Well, this measure is supported exactly on the Julia set. So the Julia set, which is an invariant set, has measure 1. the Fatou set was also an invariant set. It has measure 0. So, I mean, that's sort of good that this map is in fact ergodic. It's respecting that property. And one example shows up with the Julia set and the Fatou set, respectively. Mixing is a stronger property. Again, mu is an invariant probability measure here. Essentially, what it says is if you take any two measurable sets at all, and if you take the very far back inverse image of B, so if you look at the set of so mu of A intersect phi inverse n, phi minus n of B means what is the chance that a given point X is both in A and its nth forward image is in B. So what is the chance of that happening? And basically that's the product of the chance of a point being in A times the chance of being in B. So the idea is there's sort of being in A or some future iter being in B or probabilistically independent events. And somehow this means that the map is sort of really mixing the space around. Ergodic also kind of means it's really mixing the space around too in some hand-wavy sense, although with a little less emphasis on the word really there. So it turns out, ergodic theorists know well that mixing implies ergodic. But by the way, the proof of mixing is actually much more advanced. I'm not even going to come close to touching that today. But it is true that it is a mixing measure. So if you're an ergodic theorist, you might care. If not, you probably would not mind if you never saw that again. So, yes. So there's this recent paper. I'm not even sure if it's appeared yet. It's certainly on the archive by Rivera Letelier and Favre, of course, where it's called Theorie ergodique, something like ergodic theory of rational functions in Berkovich space, something like that. And they do a lot of stuff in that. They do some pretty cool stuff in that. One other property is that so some measures like the delta measure, or any measure that can be written as stuff plus a multiple of a delta measure, can have atomic parts. That is, they might have points for which the measure of just the singleton set containing that point is positive. So essentially sort of a portion of the measure is some multiple of a delta mass at some point. So that can happen if and only if actually the measure is just the delta mass at that one point. So the only way to have a point that has any mass at all by itself is for the entire measure to be just a delta mass at that point. And that, in fact, only happens in the case that basically you have good reduction. So, or after a change of coordinates, you have good reduction. So the idea is if you have good reduction, then your invariant measure, then the Gauss point is totally invariant, and your invariant measure is the delta mass at that Gauss point. And maybe if you change coordinates, then it's at a different type 2 point. So the idea is that's the only possible way for the invariant measure to have any kind of delta mass at any point. Otherwise, it's sort of more evenly distributed with no delta masses anywhere. Again, this is not that hard to prove once you have the other properties of the invariant measure, but I'm not going to touch that today. It's in all these guys' various papers. Okay, so to construct this measure, we're going to need to talk about weak convergence. So actually, this has come up in both Sound's and Manfred's talks. They actually more correctly called it weak star convergence, which is what I'm really about to define. But for some reason, in these various non-Archimedean dynamics literature papers, they always call it just weak convergence. I don't know why they did that, but it is the same notion of weak star convergence that is normally talked about. But just because I was looking at these papers, I'm calling it weak convergence. So again, the setting is you've got a topological space and a sequence of signed Borel measures. For our purposes, you should be thinking of the topological space as being Berkovich space or the Riemann sphere. So we say that the sequence of measures converges weakly, or really converges weak starly, to another signed Borel measure. If for every continuous function with compact support, if you take the integral of f with respect to the mu n's and you take the limit of that as n goes to infinity, you get the integral with respect to the limiting measure. Okay, when I saw this, this is the kind of definition that, when I was taking real analysis in courses like that and would run into a definition like that in grad school, it would just piss me off. I mean, what the hell does that mean? It turns out this is really the right notion to take. I mean, sort of naively, if you asked me in a vacuum if I could survive a vacuum, if you asked me in a vacuum, what should it mean for for one set of measure, for a sequence of measures to approach another measure. I mean, so the most obvious thing to say is, let's take, for any measurable set, the mu n of that measurable set should approach mu of that measurable set. But here's an example. Let's take x to be r. I think we all understand the real line. And let's take our sequence of measures to be delta masses at the point 1 over n. And, you know, so it seems reasonable that that ought to converge to the delta mass at 0, right? Because 1 over n is going to 0. Well, if you do the naive notion of convergence of measures that I just mentioned, that doesn't work. Because say you could take your measurable set to be the positive real line. Every single one of these guys gives that set measure 1. But this guy gives it measure 0. Okay, so that's sort of the wrong notion if you want these guys to converge to that. You can't use this naive notion of convergence that I just hand-wavily described. You need something a little more advanced. But this notion of convergence does make these guys converge to that guy as follows. And it's very easy to check. Because for any continuous function, well, with compact support, you don't even actually need that in this case. So this here is just a copy of this, only I've put in what the mu n's are. Well, if you integrate something with respect to a delta measure, that's easy. You just evaluate the function at that point, right? Okay, so in other words, this limit here is just the limit as n goes to infinity of f of 1 over n. Now, and this is the key point, because f is continuous, which is a crucial assumption here, that's the same as f of 0, which is exactly the integral of f with respect to the delta measure at 0. So if you use this more complicated condition where you require that you're integrating only with respect to continuous functions, then you do get the convergence of the delta 1 over n's to delta 0. And that's why weak convergence is the right notion if you want this kind of thing to be true. So again, the assumption that you're integrating with respect to continuous functions is crucial to make this step right here work. Okay. All right, so weak convergence means you integrate with respect to continuous functions, and the limit of the integrals is the new integral with respect to the new measure. Okay, so here's how in all these various proofs, well, they're slightly different in how they proceed, but here is essentially how all these various proofs show the existence of the equilibrium measure, and the original proofs over the complex numbers preceded by roughly the same idea too. So you take your rational function, you want to construct an equilibrium measure for it. So start with any point in the space that's not a type 1 exceptional point, because if you started with infinity for a polynomial and you do what I'm about to do, you'll just get the delta mass of infinity, which is not what we want. So start with a non-exceptional point anywhere in Berkovich space. And what we're going to do is start with the delta measure, the delta mass at that point, and for each n bigger than or equal to 1, pull it back by another iterative phi. Well, that's going to make the mass d instead of 1, so divide by d so that you still have a probability measure. So in other words, the nth measure in this list of measures is you pull your original delta mass back by phi n times and divide by d to the n. So that will be a probability measure. That is, its total mass is 1, and the measure of any set is non-negative. And our hope is that is, that's what I'm just saying here. Mu n is a probability measure. It's a sum of deltas. It's got a delta mass of mass 1 over d to the n at every point in the nth preimage of C, with appropriate multiplicity. And the hope is that that's going to converge weakly to some measure. And that measure will be the equilibrium. Now, by the way, if you believe that it converges weakly to a measure, then the fact that the measure is the equilibrium, you sort of get for free at that point. If there is a limiting measure that these guys actually converge to, then if you take phi upper star of that measure, take the pullback of that measure, you're going to get d times that measure because of the way these guys are rigged up. Because each one of these guys is 1 over d times the pullback of the previous one. So you sort of take the limit of both sides as n goes to infinity, and you get that pullback of mu is, the pullback of mu is exactly d times mu itself. So the second part is free. The hard part is to show that the mu n's actually converge to something at all. Okay. Now, by the way, this is again why we want weak convergence here, because you're just thinking in terms of the Julia set here. So the Julia set is some crazy fractal looking set. I have no idea what it looks like. but I'm taking some point C, and then I look at its pre-images, so that gives me D points kicking around somewhere. And then I look at the pre-images of that, and that's going to give me D squared points, counting multiplicity, kicking around somewhere. And then I'm going to look at the pre-images of that, and that's going to give me D cubed points, kicking around somewhere, and so on and so forth. And the idea is, if you take any Julia point here, well, since it's Julia, if you take a little tiny disk around it and iterate that many, many times, you're going to essentially cover the whole space. So that means as I take more and more pre-images of my original point C, eventually you're going to start picking up pre-images in here. So at any Julia point, as you take more and more pre-images, you're going to see pre-images of C near that Julia point. And so this is why if you take all of these various, all these pre-images of C here are going to start basically accumulating on the Julia set. And so the fact that these measures, these sum of delta measures, are accumulating at the Julia set is really what's saying that these measures are converging weakly to some measure that's supported on the Julia set. So that's again why we need this notion of weak convergence as opposed to the naive convergence that I was talking about. Because none of these points probably are actually in the Julia set. I mean, if C was actually in the Fatou set, then every single one of these points is in the Fatou set. None of them is in the Julia set. So we need this weak convergence to actually get them to go to the Julia set. Okay. So again, the construction of the measure is start with a delta mass and just start taking more and more pullbacks of it divided by d to the n and hope that that's going to converge to something. All right, well, to show that it converges, you need potential theory. So you need the Laplacian. So again, echoes of Manfred's and Sound's various lectures. So for any smooth, real valued, let me complex function on the complexes, its Laplacian is, well, you've been seeing a lot of this in the past few days, just partial squared with respect to x plus partial squared with respect to y, or if you like partial z and partial z bar notation, it's that. Okay, so as I think probably both Manfred and Sound mentioned, you get the integral of g times delta f is equal to the integral of f times delta g for any sufficiently smooth function g. Okay, that's great, except this is all assuming that f is C2. And that's too strong for our purposes today. So, oh, sorry. I forgot to mention one thing, just so you know intuitively why this is true. So this can be proven pretty straightforwardly using Green's theorem, but to see it intuitively, I mean, just think in terms of integrating over R. I mean, you're sort of integrating g times the second derivative of f. Well, by integration by parts, and Manfred went through this yesterday, why you don't need the first term, because you got compact support. That's the same as negative, well, differentiate the g and integrate the f, so negative f prime g prime, and then do it again, and you get positive f g double prime. And that's sort of the intuitive idea of why this is true. But again, the real proof uses Green's theorem. All right, but like I said, the assumption that f is C2 is that's too much of an assumption for me today. So I still need some notion of how nice f still can't be just totally arbitrary. I don't want to get into exactly how nice f needs to be, but it definitely does not need to be smooth. It turns out that there is a unique measure such that if you do, and this measure is called delta f. So the idea is the original Laplacian of f, you should really think of it as a measure, namely Laplacian of f times Lebesgue measure on the complex line. So it turns out that given a more general f, you can construct a measure that is somehow analogous to the old Laplacian of f times Lebesgue measure, a new measure such that this same equation holds true for all sufficiently smooth g. This is essentially by the Riesz representation theorem. If you really know this stuff inside out, you'll know that the Riesz representation theorem talks about the test functions you integrate with are just continuous, not smooth. So there's some analytic trickery you need to do to make it all work. But it's essentially just the Riesz representation theorem. This side makes perfect sense for a sufficiently smooth g. And it's a linear function. Given this spits out a real number that depends linearly on g, and so that means this is a linear functional, and so that means it actually comes from some measure. That's what the Riesz representation theorem says. And so delta f, del f is that measure. It's defined to be that measure. Again, you need F to be nice enough, whatever that means, which I'm not going to say, to make all the analytic trickery that you need to invoke the Riesz representation theorem to work. But if what I just said didn't make sense, never mind. The point is that there is given a sufficiently nice, but definitely not necessarily smooth F, there is a way of making a measure which is somehow analogous to the Laplacian, the traditional Laplacian. To give an example, so log of the absolute value of z, we know this to be a harmonic function. I hope that's it's the real part of the complex logarithm function. Except at the origin, it's got a serious problem, right? I mean, that's definitely, so it's not harmonic at the origin. Well, if you take the Laplacian of that, you get 0 everywhere, except you end up getting a delta mass at the origin. Or well, 2 pi times the delta mass at the origin. And I'm not going to prove that. That'll be homework or something. So then another thing is, here's another function you take. Please note, this is really not smooth. I mean, this is continuous maybe. It's now defined everywhere, but this is highly not smooth along the unit circle, where you suddenly change from log of 1, so 0, to log of the absolute value of z. But you can still take the measure value Laplacian of it, and it turns out you get Lebesgue measure on the unit circle. Again, you can see this is constant 1 inside the unit circle, so it makes sense. This differential operator there gives you flat 0, and it's harmonic strictly outside the unit circle, where it looks like log of absolute value of z. So the Laplacian gives 0, but right on the unit circle, exactly where you had this non-smoothness, you end up picking up Lebesgue measure on the unit circle. By the way, what's really going on here, I was talking on C. Really, you sort of ought to do this over the full Riemann sphere. And in both of these cases, you actually pick up a minus 2 pi times the delta mass at infinity as well. So if you really were working on the full Riemann sphere, you'd actually pick up the total mass of this new measure delta F would actually be 0, because you get a mass of 2 pi here, either just at the point 0, or in this case, all along the unit circle. And you cancel that out with a negative 2 pi mass at infinity. Okay, this is, I got this essentially out of this wonderful book on potential theory by Ransford. It's, like 200 pages. So this is that 200-page book in one slide. All right, so let's do this over on P1. So it turns out that there is a metric on the Berkovich space, which doesn't, I cannot emphasize this enough, does not induce the metric topology. Does not induce the Berkovich topology, the Gelfand topology. But there is a metric on the space, or at least if you remove the type 1 points. So let's say you got here's a sketch of P1 of the Berkovich space. So the idea is that the distance from, say, this point is zeta of AR. And this point up here, let's say, is zeta of AS. So centered at the same point A, but different radii. So that corresponds to, zeta of AR corresponds to the disk of radius R centered at A, and zeta of AS corresponds to the disk of radius S centered at A. All I'm saying is the distance between these 2 points on the tree is just simply the log of the ratio of these 2 radii. So I don't know if you remember from complex analysis, this is a sort of an invariant of an annulus. If you make a conformal change of coordinates on an annulus, it'll screw around where the annulus is and maybe what the radii are, but the ratio of the radii is preserved. And it's called the modulus of the annulus is the logarithm of that ratio of the radii of the annulus. So this is the exact same thing. So the distance between 2 points in Berkovich space is just the modulus of the corresponding annulus. So it'll be if there are different points, this will be some positive thing. And according to this metric, the type 1 points are infinitely far away. So that's why they're sort of not. That's why I removed them from Berkovich space. So for example, no, let me not say that point. Anyway, so the point is there's a metric. Again, the metric topology, this does give you a metric topology on this, but it is definitely substantially stronger than the Gelfand topology. So I want to doubly emphasize this metric does not induce the Gelfand topology, but it is a useful metric nonetheless. All right, so now again, I'm going to brush under the rug exactly what nice enough means. For instance, when Matt Baker gave a talk at the same winter school a few years back, He went through much more carefully exactly what nice enough means, but I'm not going to bother with that. He gave 4 lectures talking about that. I have about 20 minutes left. So given a nice enough real valued function, and actually we're allowed to take on the values minus infinity or infinity. So extended real valued function from the Berkovich space to the real line. Here is, I'm not going to give a formal definition of the Laplacian of f, but here's an idea intuitively of what it's doing. So given any point, so some point zeta, you have all these directions you could go. Let's call this direction suggestively u with a little vector type notation over it. You've got all these directions you can go from zeta. So you can define a directional derivative of f at the point zeta in the direction of a given direction u to be, well, this is the standard formula for the directional derivative. The reason I have quotes around the equal sign is, what the heck does zeta plus hu mean? I mean, that's not, we can't add on Berkovich space. This is not a ring or field or anything. What I mean by that is start at zeta and go in the direction of u a distance h. Distance with respect to this metric up here. Now, of course, that's not a well-defined point because remember, this thing starts branching infinitely immediately. So there's actually infinitely many points that might be referring to. But one of the things that nice enough means is that no matter how you choose that point, this limit is going to converge. So one of the things that's built into the definition of nice enough that I'm hiding from you essentially says that this limit's always going to converge even though this thing in the parentheses here isn't exactly well-defined. Okay. But the point is, intuitively, it makes sense. You start at this point, and you go some little tiny infinitesimal distance in the direction of that and evaluate the function there and do the usual limit quotient thing. So that's the intuitive idea of what the directional derivative at a given point means. Okay, so now what you can do is, if you take the set of all directions at that point, you compute the directional derivative in the direction of every single one of them. Now, by the way, again, the nice enough here, all but finitely many of those are going to be 0. So there's only going to be finitely many directions where the directional derivative is non-zero. So this is really a finite sum here. So what you do is you define the Laplacian of f, which again is a measure. A portion of it is going to have a delta mass of total mass. So multiply the delta at zeta by the sum of the directional derivatives in all directions. Now, by the way, what generally happens is what will often happen for one of these nice enough functions f is f will be increasing as you move, say, vertically here, but it will be constant off every single one of these side branches here. So if that's the case, if f is just nicely increasing as you move up this vertical line here, well, you're going to get a negative directional derivative coming in from the bottom, and you're going to get a positive directional derivative going out the top. So actually, a lot of times, this total sum will add up to 0 because most of the directions you'll be constant. Some directions you'll be coming in, the other directions you'll be going out, and they might all add up to 0. So, but not always. I mean, if there's sort of a sharp corner that happens here, then you won't get sum to 0. Meanwhile, so that's how you can pick up delta masses as part of your measure. If you have the sum of the directional derivatives does not add up to 0. Also, along segments, say from between these 2 points, from zeta of AR and zeta of AS. Well, that segment is, remember, this space is path connected. That segment is homeomorphic to some segment in the real line. And in fact, according to this distance here, it's actually not just homeomorphic, but it's isometric to the interval from, well, not r to s, but log r to log s on the real line. So just equip that with Lebesgue measure in the obvious way. So you can think of now f, at least if you restrict f to just this little segment from here to here, you can think of f as being a function from the good old real valued interval log r to log s to the real line. And you just take the second derivative of that function. So this is a Calc 1 problem now. Once you've changed it into this real interval, this is now something your Calc 1 students can understand. They just take the second derivative, well, I guess, and multiply it by Lebesgue measure. So now you get that contribution to, you do that in Calc 1, right? So now you have that kind of contribution to the Laplacian measure. So again, there's some other sort of funny cases that can arise, but so I'm brushing a lot of stuff under the rug here. But the intuition is you can pick up delta masses by this kind of sum of the direction, if the sum of the directional derivatives is not 0, and you can pick up Lebesgue-like pieces along segments if the second derivative along that segment is non-zero. Okay. So the intuition here is you should think of Laplacian of F as being a description of where the electrical charges are if the voltage, so think of this as a big, electrical circuit, well, except there's no loops, but a bunch of wires, and it's the entire universe, and the total charge in the entire universe is zero. But you have a bunch of protons and electrons or something somehow distributed in this massive thing, and you don't know exactly where they are, but you have a voltmeter, so you can see what the voltage is at any given point. If F is a description of what the voltmeter reading is at every point, then Laplacian of F tells you where the electrical charges actually were that gave you that voltage, and they could be positive or negative and stuff like that. But because this is your entire universe, the total charge in the whole universe, counting positive and negative, is zero. So if you have a delta mass somewhere of mass 1, you got somewhere else total mass negative 1 to cancel it out. All right, so let's see some examples just to fix some ideas. So here's a perfectly reasonable function. We saw this over the complexes, the log max of the absolute value of z in 1. So the analog for that officially, remembering that points in the Berkovich space are semi-norms, technically take the semi-norm at zeta of the function z and take the max of that in 1 and finally take the logarithm. But I mean, intuitively, that's just the log max of the absolute value of zeta, comma 1. All right, so what does this look like? What does this function look like? Well, here's the Gauss point. So below the Gauss point, all the branches coming off the Gauss point, there you have the absolute value of zeta is less than or equal to 1 in this region. And so that means that f of zeta is 0. So at the Gauss point and all of the branches extending beneath it, this function here, f, is just constant 0. Now as you move up the segment that heads up towards infinity, along here, so let's say this is zeta of 0r, well then it turns out that f of zeta of 0r is, using this formula here, is just simply log r. Okay. And if you go on any side branch coming off of this, all along here on this whole side branch, f is also equal to that same constant value, log r. So you can check all this. It's not too hard to check that that's what this particular function looks like. So that's what I'm saying here. It's constant on the Berkovich ball, on the closed unit Berkovich ball. I guess I used t here instead of r when I'm on the slide. But f of a given zeta of 0t is log t for t bigger than or equal to 1. And it's constant along any side branch. All right, but please note what I'm saying here in this comment here is that remember that the metric along here from along a segment in the Berkovich space is like a logarithmic thing. Okay, so really, if you think of what f is doing, this interval here is isometric to the interval from 0 to infinity in the real line, not from 1 to infinity, where the metric is r. So what you have is the function there is given by f of x equals x. I said log t initially, but remember the distance along that line is already given by log t. So in other words, all the main action of this function is along this vertical segment from the Gauss point up to infinity. And there it's just giving that the point that's distance x from the Gauss point, f of it is just x. So this is once you think about it that way, it's a relatively boring looking function. So it's easy to check then that at the Gauss point, you pick up a delta mass of mass 1, because all of the directional derivatives along any of the branches heading out of the Gauss point southward are 0, because you're just constant value 0 along those. So the directional derivative is 0. But as you head up this way, then you have f of x is x, so suddenly you have slope 1, so you pick up a directional derivative value of 1, sum all those directional derivative values, you get 1. So you get 1 times the delta mass at the Gauss point. Everywhere else, you're sort of locally constant. At some arbitrary point along here, yes, you have a directional derivative of 1 as you go up, but you have a directional derivative of minus 1 as you go down. So the total directional derivative around any point here is 0, and on any side branch, you're constant, so again, you're 0. But at infinity, there's only one direction to go, which is down. And as you go down, again, you have, where did it go? F of x is x. Heading downward, then the directional derivative is -1. So you pick up a negative delta mass at infinity. Again, so please note the total mass is 0. You've got, and the Laplacian of this thing is just a delta mass at the Gauss point minus a delta mass at infinity. Okay. And if you didn't follow any of that, the point is you can rig up a function whose Laplacian is just the difference of two delta masses very, very easily. Okay, here's a more complicated looking function. That looks like a horrible mess. Let me tell you what that says. Please, yeah? Oh, infinity is the type 1 point at infinity in Berkovich space. Yes, yes, it is. Yeah, so I brushed some details under the rug about. I didn't tell you exactly what you do to compute whether or not there's a delta mass in the Laplacian at a type 1 point. And there's a similar sort of formula you can do. And yes, that was a detail that I definitely brushed under the rug. I can tell you about it afterwards, but I can't possibly tell you about it in a finite amount of time. But the point is there is a because it being infinitely far away. So, but yeah, there is a perfectly good way to define it. And yes, you're absolutely right. I'm brushing some details under the rug, but it turns out that that's what it gives you is negative delta mass in infinity. Okay, so for the second function, it's the same idea. Again, in this function right here that I was just describing, all of the action was happening along the segment from the Gauss point up to infinity. So the second function, this g here, is the same kind of thing. Now I've got an s value is now less than 1. So all the action is now going to happen on the interval from the Gauss point down to this, well, I guess type 2 or type 3 point at zeta of 0s. This time, if I view the interval from 0 to infinity as the extended real line, the origin now corresponds to the Gauss point, but just good old x and y axes here. What's happening now is this thing is saying, so for t bigger, oh, I guess I used t instead of x. Sorry about that. For t bigger than 1, that is to say, if log t is bigger than 0, then g of log t is just log t. So actually, I labeled it t. I really should label it log t. If I am working at the point that is distance log t above the Gauss point, the f of it, I should say f of zeta of 0t, is just log t. So it looks like f of x equals x along that. Meanwhile, now log s here is negative because s was less than 1. I get just a constant value. That's what this says right here. So if t is less than s, if log t is less than log s, I'm just getting some constant value. And then this thing in the middle is a quadratic in log t, so it's just whatever parabola connects these things. I mean, that's the official formula for it, but it's the parabola that connects these things so that the tangent lines are smooth at both points. So it's got a horizontal tangent line here, and it's got a tangent line of slope 1 here. It's just whatever parabola fits that. Okay, well, if you check now for that guy, because the directional derivatives now at any point are the same going in as going out. Because at every point, the tangent slope backwards exactly is going to match the tangent slope going the other way. So we don't pick up any delta masses, except at infinity, which for the same reason that I brushed under the rug as before, we're going to get delta mass of weight -1 at infinity, essentially because the slope is -1 as you head backwards. I'm sorry. And then off all the side branches, just extend this function g to be constant at whatever value it is off the main tree trunk. Then it turns out that the Laplacian of this thing, again, like I said, you get a contribution of negative delta mass at infinity, and then all the action happens during this curvy part from between these 2 points here, where because this is the case where you pick up the second derivative business. And so you end up getting the second derivative. By the way, please note -1 over log s is positive because s is less than 1, so log s is negative. So -1 over log s is a positive quantity. And you're multiplying that by Lebesgue measure along this segment here. So this guy here, its Laplacian just looks like Lebesgue measure along this segment and 0 everywhere else. Okay, so this is the kind of thing the Laplacian operator, this Berkovich Laplacian operator does. Again, there's a formal way of defining it that's much more general, blah, 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 blah. But I just want to give you some idea of what can come out of this. It turns out that the Laplacian operator is linear. The Laplacian of a function is 0 if and only if the function is constant. Well, if you combine those two things, the two Laplacians are the same if and only if the original function is deferred by a constant. So again, it has the feel of a differential operator. We don't need this, but just for kicks and giggles, it turns out that if you integrate f with respect to the Laplacian of g, it's the same as the integral g with respect to the Laplacian of f. One thing we do need is that if you pull back the Laplacian measure of f by some rational function phi, you get the Laplacian of f composed with phi. So this is going to be important for us. Everything else above this is garbage for us, but this one's important. The other thing, and this is the real reason we need this is why we brought this into it, is that if you have a sequence of functions uniformly approaching another function f, then the corresponding Laplacians converge weakly. And this is why we really need this, because figuring out whether one measure converges to another measure weakly that's hard. Figuring out whether one function converges to another function is relatively easy. Now, by the way, these conditions here can actually be relaxed. I mean, I've got uniform convergence and I need some kind of uniform boundedness condition of the measure. In fact, you can relax those conditions substantially, but I don't. It's complicated to state exactly what the precise relaxed version is. And yes, I am running a couple minutes over. Ha ha ha. So here's how you actually prove the convergence to the equilibrium measure. So remember what we did. The idea is that we were going to choose some non-exceptional point in Berkovich space. You are actually allowed to choose C to be of type 1, but in order to use this phrasing of this convergence condition, for the purposes of this exposition, I'm not going to allow it to be type 1. But if you use the stronger version of that convergence statement, you can even allow C to be of type 1. Anyhow, what you do is if you remember from the thing I sketched before, was we set mu n to be the nth pullback of the delta mass at C divided by d to the n to make it a probability measure. So this is a sum of finitely many delta masses appropriately scaled. And so we were trying to prove that these various sums of delta measures together converge to some probability measure. And by the way, once you get that it converges to a probability measure, you get this nice invariance property for free. All right, so here's how you do it. So you choose, first of all, some real function such that the Laplacian of u is the difference between mu1, the first pullback thing of the delta mass, minus the delta mass itself. There's two ways to do this. One is you can build up this abstract theory of potentials, which I'm not going to try to do, but you really should if you want to do the theory properly. The other is, remember, I was trying, not this example, but the previous example, I showed you that you can easily rig up functions whose Laplacian is a difference of a couple of delta masses. So this is just a sum of some delta masses. This is another delta mass. It turns out by just completely ad hoc means you can write down a function whose Laplacian is that. But let me not worry about that by messing around with the kind of example I had on the previous slides. And now we're going to define a function fn to be this horrible sum. So we've got u composed with the ith iterative phi scaled down by dividing by d to the I, and sum these guys all up. Why? Because it's going to work. All right, now these things all appear on the next slide, so don't frantically try to copy them down. So that's just reminding you what mu n was, and this function u was chosen with the amazing property that its Laplacian is this thing here, and fn we decided was this. So what is the Laplacian of fn? Well, the Laplacian is linear, so that's d to the minus I times the Laplacian of u composed with phi to the I. But the way pullback measures work, if you take u composed with phi to the I and take the Laplacian of it, that's the same as pulling back by phi to the I, the Laplacian of u. Again, by that property I was trying to highlight on a previous slide. But we know what the Laplacian of u is. It's this thing. So if you put that all through, you get this big mess here, which looks like a big mess at first until you recognize that you've got d to the minus I, phi to the I pullback of the delta mass, and here you've got the same thing with I plus 1 instead of I. So this is a finite sum and it's telescoping. And so what you get is just the last term of the last term minus the first term of the first term or something like that. Anyhow, you end up getting exactly mu n, well, minus the delta mass at c. And so you know precisely what the Laplacian of Fn is in terms of mu n, but the key thing is u is a bounded function. This is something I didn't mention before, but because I made the assumption that c was not of type 1, it turns out that the mu you can write down is indeed bounded. So Fn, which is a sum of d to the minus I times mu of stuff, converges uniformly to something. This is classic, introductory real analysis. So there is some function that the Fn's converge to, namely the infinite sum. And so by the thing about weak convergence,